Hello, discrete math fans. Let's give a specific example where we'll talk about equivalence classes modulo 3. So R is the relation of congruence modulo 3 on the integers. All right, what do we mean by that? What we mean is for all m and n in the integers, m is related to n if and only if 3 divides m minus n. Now we've seen this relation before, maybe not with 3, but with other numbers. Now we're going to start using a new notation. So instead of writing 3 divides m minus n, we're going to start writing m is congruent to n modulo 3. Let's give a description of the equivalence classes of R. Let's let a be an integer, and let's see what's inside the class of a. Okay, so the class of A is the set of all integers such that x is related to A. Well, what does that mean? That's the set of all integers such that 3 divides x minus A. Let's continue to rewrite this. So now we'll rewrite it using the definition of what it means for 3 to divide x minus A. It means x minus A is equal to 3k for some k in the integers. And then if we move things around, we'll say that this is the set of all integers such that x is equal to 3k plus a for some k. All right, well, let's use some specific numbers. The class that contains 0 is the set of all integers that's of the form 3k. Those are all the multiples of 3. The class that contains 1 is everything that's of the form 3k plus 1. Class that contains 2 is everything of the form 3k plus 2. And you notice we've written out a few members of these classes so that we can see what's in there. Keep in mind that we know that 3 is related to 0, so one of our lemmas tells us that the class containing 3 is the same as the class containing 0. And by the same reasoning, all of these guys are the same class. We're giving a different element, but it's the same class. Similarly, all of these are the same class, and all of these are the same class. Now, we should also note that every integer is in one of the classes, the class containing 0, the class of 1, and the class of 2. Every integer is in one of those classes. So that tells us what the distinct equivalence classes are. All of these guys are the distinct equivalence classes of the relation. Now, if you think about it, this really is giving us a very close connection between the quotient remainder theorem, when we divide by 3, and the equivalence classes modulo 3. Okay, let's make a definition here. Let's suppose that R is an equivalence relation on a set A, and S is any equivalence class of that relation. A representative of the class is any element A such that the class of A is equal to S. Now we know that the class of 0 is the same as the class of 6. We can say both 6 and 0 are representatives of the same class. What we'll prove later on, we'll have this as a homework assignment, is that any element of an equivalence class can serve as its representative. And finally, we want to make a definition to say that if m and n are integers and d is a positive integer, we're going to say that m is congruent to n modulo d, and we'll write m congruent to n mod d if and only if d divides m minus n. So it's not a new idea, it's just a different notation, and this is a fairly common notation, so you should be familiar with it. Okay, that's all for now.